Shall I now share my screen?
Sir, sir, not needed. We are starting the session and we will be sharing all the PPTs from our side.
Okay.
So, when you will be introduced by the moderators, your PPT will be shared and then you can start.
Welcome everyone in the second session of this conference. So I would like to introduce the moderators for this session. So in this session, moderator is Dr. Pravesh Shukla and co-moderator is Dr. Gabriel T. Glasgow. Dr. Pravesh Shukla is an assistant professor in the Department of Mechanical Engineering at IIT Bhilai. Dr. Shukla received his PhD from IIT Kanpur, and before joining, he was a postdoctoral researcher in the Division of Combustion Engine, Department of Energy Science, Lund University, Sweden. His research area includes internal combustion engine, alternative fuels, and emission reduction technologies. Dr. Shukla has published more than 28 technical articles in the International Journal and Conference Proceedings. The second moderator of this session, Dr. Gabriel Glasgow, is currently research scientist at the National Research Council of Italy. His main research interest is focused on advanced technologies and fuels for propulsion and energy conversion systems. He received his PhD in Mechanical Engineering in 2012. He is the serving editor and reviewer for several indexed journals of national and international literature. He has authored more than 70 journal articles, conference proceedings, books and book chapters, and technical papers. With this brief introduction, I would like to hand over this session to our moderator, Dr. Pravesh.
Thank you, Akhilesh. Myself, Pravesh. Hello. Thank you, Akhilesh. I'm here with co-moderator Dr. Gabriel Glasgow also. So, in this session, first of all, I would like to introduce Professor A. Ramesh. Professor A. Ramesh has a PhD in the internal combustion engine from IIT Madras. He did his postdoctoral research at Ecole National Superior de Nantes, France. He is currently an institute chair professor at IIT Madras and has worked in the engine R&D group in the BEML and also an assistant professor in IIT Delhi. His research interests include engine combustion and emission control, GDI engines, HCCL engines, hybrid electric drive, engine instrumentation and control, and innovative engine technologies. He has guided several students for their PhD and master's degrees and has published more than 175 research papers in journals and conferences. He works on several projects jointly with automotive industries and has many patents. And he has received the Srimati Bharati Annapurna Gurunath Award for Excellence in Teaching from IIT Madras, Lifetime Achievement Award from SAE India, Southern Section, and the Bhagya Lakshmi Krishna Iyer Award at IIT Madras. He has served as the chairman of the Center for Continuing Education at IIT Madras. He has also served on committees in DST, MNRE, CSIR, TELFAC, DRDO, ISDICT, NITs and IITs. So, Professor Ramesh, I request you to present your lecture. Hello, Professor Ramesh.
Good afternoon. Thank you very much for the opportunity, and thanks one and all for making this happen. I'll just take a few minutes and I'll just talk about the importance of simulation and experimentation in modern engine development. So I'm just going to give an overview. We know that models describe the physical phenomena in engines and through mathematical equations. And through simulations, we integrate different models for the different processes that we have in an engine. I think the slides are not. Hello?
One second. Professor Ramesh, just a minute. There is some technical glitch in the presentation, so the person is resolving.
Good afternoon. It's nice to be interacting with all of you and share a few of my experiences to show how modeling and experimentation can aid engine research. We know that models describe the physical phenomena in any system, say in an engine, using mathematical equations, and we put together models to develop a an overall simulation model of the entire engine, and so that we can employ it for different parametric studies. So we all know that models can be zero-dimensional, where you don't have any resolution in terms of space, or you can have three-dimensional CFD models. And very often, today we find that at the level of development of internal combustion engines, one has to resort to a combination of advanced experimental techniques and computational methods. And this can enable us to save a lot of time and a lot of expenses as well, and reduces our time in experimentation. Can we go to the next slide, please? So I'm not going to go into the details. We know that an engine has so many systems. So I would generally call an engine as a system of systems. And we have the intake system, the turbocharger, the after treatment device, the dynamics of the engine, the fuel system, and so on. And all these systems have to be separately modeled, and all these systems have to interact with each other to make the IC engine run. So each one of them has its own characteristics, and how we put them together and how we enable them to match together is what is very important, and their modeling can play a very important role. And today we have also the advent of hybrid drives. So this again takes us to a different direction. Maybe it's the hybrid drive engine models are simpler, but then there's a new avenue which has been opened up today. Next slide, please. So there are lots of areas where you can see engine models being applied. I've just put a few here: turbochargers, prediction of engine temperatures for starting, modeling of diesel engine combustion for real-time control, combustion chamber development for diesel engines, GDI engines, flow in GDI engines, and new piston designs to evaluate a new piston design for a GDI engine models for specifically hybrid application, then after-treatment systems, particularly under transient operating conditions, intake and exhaust system dynamics, fuel injection rate shaping, fuel injection spray modeling, and modeling of advanced combustion engines like RCCI, PCCI, etc., and simulation of new engine concepts and systems for development of models for HIL systems, and integrated engine and vehicle models today, which are very important. An engine has to work with a vehicle, so the vehicle characteristics can affect the way the engine performs. So this is also very important. Next slide, please. I'll just take a few examples from what we have been doing here. One of the examples is how ignition delay and combustion models can be used for real-time control. So you can have a physics-based ignition delay model which can simulate effects of multiple injections and spray and thermodynamic conditions, and actually predict physical and chemical delays. You can also have a model for the combustion, and these can be integrated and put inside the ECU for real-time prediction of the combustion parameters. So you could a priori, before the next cycle, decide how the next injection parameter should be. And this model can also bring inside the effect of certain geometrical parameters, injection parameters, and charge conditions. And these models can be real-time capable because they are simple, but they are robust, and they can run inside the ECU. I'm just going to show you how these models can be. Next slide, please. So I'm not going to the equations. You can see here the equations for the predicting the liquid length, the physical delay, chemical delay, and so on, and also how a CFD model has been, CFD simulation has been.
Yes, maybe you switch off your camera because the bandwidth is low coming from the.
Yeah. So you can also see how a CFD model has been running in parallel to get some information which is fed back into the phenomenological model. So we could tune the phenomenological model based on some information from CFD to predict the temperature gradients inside the cylinder, so that we could predict the ignition delay better. So you can see here how we have on one hand a simple thermodynamic model. You have a CFD model also running, information from that going inside to this thermodynamic model for tuning it better. And then you see how the real-time prediction becomes better. You can see the next slide, please. This slide shows real-time prediction of ignition delay inside an ECU. On the left-hand side, you see graphs where you see certain engine parameters being changed, like the rail pressure, the injection timing, and so on. And on the right-hand side, you see the predicted ignition delay and the calculated ignition, and the actual measured ignition delay on a cycle-by-cycle basis. So you can see during engine operation, the whole calculation takes only 1 millisecond with all the parameters actually coming from the engine. There is no other parameter which is an input to this model except engine sensor information. So with engine sensor information, you are able to predict the ignition delay. And when you predict the ignition delay, you can tune your injection parameters so that you can adapt to that ignition delay and get better combustion facing. So this is one example of that. Next slide, please. Another very useful area where CFD models can be used in the development of engines is combustion chamber design. You see here that you can quickly evaluate any concept that comes to your mind and evaluate different combustion chamber shapes and then see how they perform through your CFD models and then apply them to the actual real world. And this reduces the number of experiments that we need to do. And we see that we have in our own experience seen that it aids combustion chamber development significantly and reduces a lot of time. So this is another big area where a model can be directly applied to a physical, for really designing something. Next, please. We have also used it to arrive at fuel injection strategies for GDI engines, also predicting some, developing some new injectors where you have twin mode injectors, an injector which can perform with a narrow spray for stratified charge running and a wide spray for homogeneous charge operation. So you can, we actually use this for developing an injector and then actually made the injector. So you can see how from a CFD study, you can actually go to developing something. Next, please. This is another concept which we had for enabling cold starting under very low temperatures, particularly at low compression ratios. You can see here there's a lot of mechanisms involved. We have a hydraulic mechanism. We also have some thermodynamics involved in increasing the temperature of the charge by recompression. So we could model all this. It was a sophisticated model where we could link everything, and ultimately we could predict the rise in temperature that you can get with this mechanism, and it was actually implemented. So to enable cold starting of low compression ratio diesel engines. So this again is a one-dimensional model which was linked to mechanisms, and then we could predict, as we can see in the next slide, the rise in temperature with cycles at a very cold condition, so that you raise the temperature and then you can ignite the fuel and enable cold starting even at low compression ratios. Next slide, please. So we saw an overview of how models can be used. And thermodynamic models are simple, they consume less time, they are robust if they're tuned properly with careful experiments, and they can be used for real-time control. On the other hand, CFD models are sophisticated, they allow us to make comparisons of different concepts, and they enable us to reduce experimentation time significantly, and allow us to even, if you have a bright idea, you can immediately implement and see whether you're going in the right direction or not. And thermodynamic models and CFD models go hand in hand, because many of the boundary conditions and etc. for the CFD model can be got from thermodynamic models. Thereby you can save time. So models, experimentation, 1D, 3D, all have to go together if you really have to put them together in developing an engine. This is what I would say in conclusion. Next slide, please. So I'd like to acknowledge the support we have received over the years from all these to actually come to whatever I'm saying today. Thank you very much.
Thank you, Professor Ramesh.
Thank you.
For audience, we can take the question at the end of the presentation session.
Sure.
I would like to move to the second presenter now. I welcome Professor Jacek Junik. Professor Jacek Junik is an associate professor and head of powertrains laboratory at the Ludwig University of Technology, Poland. His track record includes experimental engine research and renewable low carbon fuels. In the area of combustion research, his studies are centered on the control strategies for low temperature combustion in LCCI engines, including the MDO fuel reforming. With over 23 years of professional experience in combustion engines and powertrain development, Professor Junik is a grant holder of several relevant nationwide projects funded by the Ministry of Science and Higher Education and National Science Center, Poland. He is a member of several international research groups. He is also an innovation innovation consultant for domestic off-road vehicles and bus manufacturer, posters, and technical advisor to the Polish military industry in the field of power. Since 2018, he has been a Polish scientific society. He has been in the Polish scientific society for combustion engines as a combustion engine board member. So, Professor Yunich, I request you to deliver your presentation.
Thank you. I hope you can hear me.
Yes.
Thank you for your kind introduction. It's a pleasure to speak to you today. I only regret I'm not physically here. So the goal of my speech is to shed some light on multi-zone approach to modeling of low temperature combustion. This is a new hope for internal combustion engine. This technology can be applied for different engine platforms and used with different biofuels, clean combustion with extremely low PM and NOx emission, plus carbon neutral fuels can provide truly sustainable powertrains. Importantly, the solution can be provided now. We don't need to wait 20 years or so. I will not comment this well-known graph, but I will comment one aspect. Although low temperature combustion seems to be easy, it is very difficult to control it. May I ask for next slide, please? Next slide, please. Thank you. So we can say that we have all hardware tools to apply low temperature combustion, but the complexity implies that number of control parameters is so high, is much higher than in conventional engines. So the experimental approach must be supported by modeling. So next slide, please. It should be noted that larger simulations takes even more time than experimental research, but halfway between complex CFD models and simple, let's say, experimental empirical correlations, there are multi-zone models which are simplified but fast. On the other hand, low temperature combustion is premixed and is mainly dominated by oxidation kinetics and temperature distribution. So there is a let's say, space for application of multi-zone models in low temperature combustion. Please, next slide. And the idea of multi-zone models is that combustion chamber is divided into homogeneous spaces. The number of zones can be from 2 to 10s. There can be different configurations. In the so-called balloon configuration, the zones lack shape, and for example, for onion skin configuration, the zones are ascribed to some physical positions, and also that there can be different interactions between zones. Please, next slide. Multi-zone models are usually running during the main combustion event and usually are coupled with other models which provide initial conditions. It can be non-reactive CFD simulations which provide temperature distribution and concentrations of, for example, air and recirculated exhaust. However, depending on the purpose, the models can be also can be also used with simple gas flow models. For example, if we need to simulate multiple cycles. Next slide, please. Now I would like to show off one of our research work package. For some time, my and my research group has been testing experimentally gasoline HCCI combustion with exhaust gas trapping. We also investigated fuel reforming by fuel injection into retained residuals. Generally, fuel reforming was found to produce reactive species, which improved combustion stability at low loads and also reduction of emissions. Next slide, please. And the idea of negative valve overlap was transferred to reactivity-controlled compression ignition concept. A multi-zone model was a tool which demonstrated applicability of this technology to improve combustion efficiency. Actually, the purpose was to reduce so-called methane slip, which is a serious drawback of RCCI engine fueled with natural gas. The model was validated on RCCI engine with variable valve actuation, and it was found that combustion can be replicated quite accurately. The next slide, please. A little bit worse was accuracy for NOx and CO emissions because they are very sensitive to local temperature and local concentrations. However, methane emission was simulated with quite good accuracy. Next slide, please. Our simulations show that the injection of some amount of fuel into retained residuals in RCCI engine enables substantial reduction of methane slip. Moreover, the fuel injection into retained residuals enabled additional control of intake valve closing temperature. Okay, next slide, please. And finally, I would like to tell about our project, which we are realizing with Finnish University of Vaasa. The project called Clean Propulsion Technologies is aimed at development of RCCI technology for stationary and marine applications. And within this project, among others, we will apply the developed using modeling technology of fuel reforming with negative valve overlap on the full metal marine engines. And the next slide, please, which is the last one. Thank you for your attention. And at the end, I would like to advertise our paper. The paper submitted and actually now after revision was submitted to Progress in Energy and Combustion Science at the same title as my today's presentation. And should be, this is very, very elaborative and contain my presentation plus much more in one source, and I hope it will be available soon. So thank you again. Thank you very much.
Okay, thank you, Professor Jason. So I will come back with some curious questions to discuss with you. Let us hear the other presenters also. So the third panelist, I would like to invite Professor Burak Zinzi. So Dr. Burak Zinzi has been working at the Marine Engineering Department of Maritime Faculty in Istanbul Technical University since 2013, and he has been an assistant professor since 2020 at the same department. His research area are alternative marine fuels, performance and emission of marine diesel engines, decarbonization methods and technologies, and energy efficiency of ships. His MSc thesis is on the application of hydrogen as marine diesel engine fuels, and his PhD thesis is on an alternative fuel assessment model for ships and experiments on the effect of ethanol on diesel engines. He is currently working on the alternative marine fuels such as ammonia, biodiesel, and electrofuels. So, Dr. Burak, you may kindly switch off your video and deliver your presentation.
Thank you for listening me. Can you hear me?
Yes, sir, we can.
Yes, we can hear you.
Okay. I want to thank you for inviting me to the conference. Today I'm going to briefly explain why engine modeling is important for large bore marine engines. First of all, we need to give answer to the question, why do we use engine modeling? Modeling studies are successful in offering convergent solutions with a better understanding of the effects of complicated systems and predicting the results. Also, highly detailed and highly accuracy results can be obtained by the modeling approach with the help of the basic operating principles of the systems. I mean, the systems is engine, of course. So we have governing equations, empirical formulas, and some data of the operating conditions of an engine to model specific conditions of the engine. Next slide, please. Okay. Benefits of engine modeling are developing a more complete understanding of the process inside the engine, less costly experimental development if efforts by identifying key controlling variables of combustion and flow processes, predicting engine behavior under various design and operating variables, and this results in developing new hardware for the engine or optimizing the design and control of the combustion process, and also provides a rational basis for new designs and developments, also using new alternative fuels. Next slide, please. Marine engines are actually larger than the regular land vehicles. They are large bore marine engines, and we have some dynamics, such as International Maritime Organization. So we need to comply with the regulations of this organization. These regulations are for CO2, NOx, SOx, and PM emissions. The limits for NOx, SOx, and PM are at the lowest level that marine engines can hardly comply with them. It's extremely strict right now. And for the CO2 emissions, IMO has the initial greenhouse gas strategy that aims 50% CO2 reduction in 2013 and 70% CO2 reduction in 2015 from the 2008 emission levels of maritime transportation. And also the strategy aims zero carbon emissions from maritime transportation. Also, we have an engine development process includes energy efficiency improvements, engine component improvement, and alternative fuel application area. The regulations and engine development is for to achieve more efficient and greener marine diesel engines and cost reduction due to the reduced fuel consumption. Next slide, please. Most of the engines at maritime transportation are large bore diesel engines if we don't consider small ships. And the specifications of some of the specifications of these engines are two-stroke diesel engines, low and constant engine speed, usually under 130 RPM, constant engine load, high engine torque to provide required thrust of propeller, larger bore diameter and longer stroke, scavenging area at the bottom of the cylinder rather than intake valve at the top of the cylinder. So you need to model scavenging area and the process at there. As you can see at top of the slide, there is the world's largest marine diesel engine, and it is in the Guinness World Records. It is a Wärtsilä RT Flex 96C. It has a length of 27 meters and 30.5 meters high, and it weighs over 2,300 tons, and its bore is 9 96 centimeters. And this engine powers the ship. Is named Emma Merce. It's at the bottom picture. It's the world's biggest container ship in the world. Next slide, please. Benefits of engine modeling for large bore marine engines. It is the efforts of engine manufacturers during the engine development process, reduce time requirement and cost of experiments with large bore marine engines. Large bore marine engines are not as flexible as smaller engines to try newly developed engine components. So these components can be tried on the model engine. Engine modeling can show the improvement areas on the engine to increase engine efficiency of large bore marine engines. And last but not least, improvement on the combustion parameters can be done, or low carbon, zero carbon alternative fuels can be tried on the engine models to cope with strict maritime emission regulations. Next slide, please. Conclusions of this slide is modeling is a necessary tool for the development of more efficient and environmental friendly large bore marine engines. Combustion modeling, fuel spray modeling, in-cylinder gas exchange modeling, heat transfer modeling, and associated components modeling are some of the modeling types for large bore marine engines. Engine modeling provides profit to the maritime industry by reducing manpower, effort, time, and cost. Next slide, please. These are my references for preparing this slide. Thank you for listening.
Okay. Thank you, Dr. Pura. So I will go to the next panelist, Dr. Amir. So Dr. Amir Aziz graduated from the Faculty of Mechanical Engineering, University of Technology, Malaysia in 2008. After receiving his master's degree in Mechanical Engineering at the University of Technology, Malaysia, he joined the Faculty of Mechanical Engineering in the University of Malaysia, Pahang in 2011. In 2020, he completed his PhD entitled High Octane Number Fuels in Advanced Combustion Modes for Sustainable Transportation at the Division of Combustion Engines, Department of Energy Sciences, Lund University, Sweden. Then he joined the Faculty of Mechanical and Automotive Engineering Technology, University, Malaysia, Pahang in 2020. As a senior lecturer, his primary research interest includes combustion, internal combustion engine, alternative fuels, and propulsion system. So, Dr. Amir.
All right. Thank you very much for this opportunity. So I think everyone can see my screen, right?
Yes.
All right. All right. So first of all, thank you again. And today I'm going to share with you some of the results from my previous research. So this is about the auto ignition characteristic investigation using modeling techniques. So my name is Amir Aziz. I'm from Faculty of Mechanical and Automotive Engineering Technology, University of Malaysia Pahang, from Malaysia. All right, so first of all, we go through the type of combustions. So we know that we have these three types, the main types. So this one is proposed by Ben Johansen. So first one is spark ignition. So spark ignition has premixed flame propagation. In the SI engine, commonly we use gasoline fuels, which we rank the fuel using RON and MON. Higher RON, meaning that the fuel has higher resistance to the ignition, while for the compression ignition, it has the diffusion flame. And in CI engine or compression ignition engine, the fuel should auto-ignite as fast as possible after the start of injection, and they were ranked using CT number. The higher the CT number, the easier the fuel to ignite, or in the other words, high reactivity fuels. While for ACCI, which has a bulk of auto ignition of a premix charge. And then we know that for HCCI or low temperature combustion itself, commonly use gasoline like fuels, because the fuels with high octane numbers, which refer to the gasoline fuels, will be the best candidates actually for the low temperature combustion. And then as I mentioned before, RON and MON, which used by to indicate the characteristic of gasoline. And then we know that auto-ignition quality of gasoline is measured in a CFR engine by adjusting the compression ratio to achieve a certain knock intensity. Nowadays, just make sure that, all right. So nowadays, actually, most of the modern spark ignition, which is SI engines, systems have direct injection and air intake boosting, which means that RON and MON octane rating system may not relevant for the current engine. And then many researchers have argued the capabilities of RON and MON to describe auto-ignition characteristics in advanced combustion concepts. And actually, there's many researchers have tried to come up with the new fuel indices, such as octane index, HCCI fuel numbers, low temperature fuel performance index, and etc. But even though they can predict some of the characteristics, but unfortunately they could not accurately describe the auto-ignition characteristic of the fuel itself. So the question is how to investigate auto-ignition characteristics. So we have, of course, two ways. We have the experiments and then, of course, the modeling. For the experiment, we can use the CFR engine, which are the same method or the same engine used for RON and MON evaluation. And then we have method engine. So by using method engine, we can know the real characteristic of the fuel. And then, of course, we go to the third method under the experimental investigation, or by using optical engine. All right, so by optical diagnostic, we can see how the behavior inside the combustion. But however, there's some limitation of these three methods, which we can compensate by using modeling. Okay, so the result from modeling technique actually can compensate with the result of the experimental works, which can contribute to a better understanding of the overall process. Okay, let's see how this example, the optical study on low temperature combustion. So this is from Sarah Lon in 2017. So on the left picture, so we have the piston, okay, for optical piston, and then the first picture indicates the spray image of the fuel, and then the second image is the ignition image. Okay, the ignition. So if you see the lights over here is the location of the ignition, and then the location of ignition is translated to this picture or to this figure, which is the radial location of initial combustion on the y-axis, and then the start of injection on the x-axis. So this is actually the range or the what we call it, a lot of experiment or a lot of combustion over here happens. I mean the cycle, different cycles actually here over here. And then we want to highlight here is the black line here actually represent the location of the piston bowl edge, and the top over here is the squish region. You can refer to this figure at the bottom right corner, the squish region, and the bottom corner is the piston bowl. All right, so we can see here is the location of the initial combustion actually goes to the squish region when at a certain area, and then we still not understand why it's happened. And then the second experiment here is about the auto-ignition of gasoline, which is we are using the rear engine. So the first one I just show you is the optical engine, and this one is the rear engine. And then what we found here is by using different fuels. Actually, you can see refer to the paper mentioned above on the right bottom corner, and this is the RON 65 and RON 90. So we have on y-axis is the RON number, and the x-axis is the ignition delay. So we can see here is the ignition delay between RON 65 and RON 90. We only have 5, and then when it goes to run 95, we have the ignition yield up to 70. So there is a huge difference. So we want to see and want to understand why it's happened. Then we come up with the CFD simulation works. We want to investigate by using the experimental data and try to validate the simulation that we have using this graph. Okay, the heat release, a comparison of in-cylinder pressure and apparent heat release. And then we want to see the spray targets from the simulation results. So we figure out that the lower run fuse injection inside the piston bowl, but the higher run fuse, which is we require advanced injection timing, injection towards piston bowl edge and squeeze region, as well as the higher PRF 97. So based on the figure, the spray target in the lower fuse, the injection was made inside the piston bowl, and then for higher run fuse, spray target outside the piston bowl. And then let's see here the fee and other results. Okay, so we figured out that actually when we have the piston, the spray injection on the piston bowl edge, we have the piston spray.
Hello.
I'm going to finish my slide. So we have the spray injection. All right. So I would like to conclude that the fuse spray piston interaction affect the auto-ignition and combustion characteristic of combustion gasoline engines, and then gasoline fuels and modeling techniques compensate the result from metal engines, and then better understanding of auto-ignition characteristic can be achieved by using modeling technique. So that's all my presentation.
We appreciate your financial support and collaboration.
Thank you.
All right. Thank you very much.
So now I request Professor R. Santosh. Dr. R. Santosh completed his PhD at the Institute of Science, Bangalore in 2016. In ISC, he worked with Professor Saptarshi Basu on aspects related to the soil flows and planes and combustion instability. Later, he moved to Rolls-Royce University Technology Center at the University of Nottingham to work as a postdoctoral fellow. Later, he worked at the Gas Turbine Research Center, GTRC, at Cardiff University in UK. For another course of experience, he joined IIT Harvard as assistant professor in 2018 and moved to IIT PhD in 2021. His research interests are experimental combustion using laser diagnostic, automation, and springs, and CLV. So I request Dr. Santosh to deliver his presentation.
Thank you for your kind introduction. Thanks for the opportunity to talk over here. I would like to briefly describe some of the laser diagnostic techniques that are employed in combustion in space. So I'll try to give an overview. By laser diagnostics, I mean employment of laser to quantitatively measure velocity, temperature, species concentrations in both reacting and non-reactive field. One of the main advantages of laser diagnostics is that it's non-invasive, meaning that the flow is minimally disturbed, and we can make transient measurements if we can make use of high-speed lasers. Apart from that, the users need to be very take a lot of precautions, because most of these involve glass core lasers, and also these diagnostics are pretty expensive. So the combustion measurements can be broadly classified into making measurements of temperature, species concentration, velocity, and so. And for the first couple of measurements, we have a bunch of techniques as described over there. And the velocity techniques are classified based on whether we make point velocity measurements or field velocity measurements. And in SUP we have LII. And apart from all these things, we have a separate class called emission spectroscopy measurements, where well-known chemicals in CH and OH fall into, which I will not describe here as they do not involve laser. In the spray measurements, the popular techniques are shadowgraphy and phase Doppler. So before I go and describe some of them in a little bit of more detail, I would like to now talk two important phenomena related to these techniques. That's one is scattering. What do I mean by scattering is that when an electromagnetic wave impinges a material obstacle, this obstacle could be a droplet or a particle, it sets the electrons into oscillatory motion. And as such, these accelerating charges they emit radiation, EM radiation, electromagnetic radiation. So basically, scattering is nothing but re-radiation due to excitation. Depending on the wavelength of the scattered light, the scattering can be divided into two types, elastic and inelastic. And in elastic, you have the wavelength of the scattered light to be equal to incident wave, where in inelastic, that's not equal. Further, the elastic scattering can be divided into Rayleigh and mean scattering depending on a scattering parameter that's just mentioned at the bottom. So basically what it means, broadly speaking, if the diameter of the obstacle is less than 1, then we call it as Rayleigh scattering, and if it's greater than 1, it's called as mean scattering. So just give you an example of how they differ. If you think of a laser beam fired into a closed dark room, all the gas molecules that are illuminated in the path of the laser, that's basically Rayleigh scattering. And and in the same path, you might have some dust particles which would be shining very brightly. That's Mean scattering. Raman scattering and fluorescence are examples of inelastic scattering. While Rayleigh scattering forms the basis of Rayleigh thermometry, Mean scattering forms the basis of diagnostic techniques like PID, LDV, and PDI. Raman scattering and fluorescence form the basis of Raman spectroscopy and LIFT respectively. I wouldn't deal much into the absorption. I would probably go and take some of these laser-based diagnostic techniques that I want to talk about today. The first one is Rayleigh thermometry. So, Rayleigh thermometry is used to measure temperature distribution in flames by measuring the Rayleigh scattering from the gas molecules. So, basically, on the left-hand side, you can see a schematic wherein a solid-state NDR laser has been fired into reaction volume, and the scattering from it is being measured by an ICC camera placed 90 degrees to the laser sheet, measuring the Rayleigh scattering. So it works on the principle that the scattering would be less if the number density or the gas molecules in the reaction volume is pretty less, and that is related directly to temperature because as the temperature increases, the gas molecules would expand and the density would decrease, and then there would be less scattering. So this methodology is the heart and soul of Rayleigh thermometry. Moving on, I would like to talk a little bit on the Raman scattering. So in order to understand the scattering and the fluorescence, it helps if you can understand. It helps if you can take the say energy levels of a diatomic molecule. There on the left-hand side, you have 0 ground level state and the first level state. So what happens in the Raman and Rayleigh scattering is that when the photon absorption occurs, the molecule, they just jump into a virtual unstable level which is in between the ground state and the first state. Okay, so that's shown in the next figure, which is shown over here. And in the Rayleigh scattering, the drop of the molecules will be to the same level, same energy level as that of the initial level. While in the Raman scattering, this drop would be to a level lower or higher than the initial level. So this is the basic difference between Raman and Rayleigh scattering. And considering that each combustion species would have their own energetic structure, so this signature of this Raman fall, Raman scattering, could be uniquely associated to each of these species. So as such, Raman scattering helps us to detect several species in the flow field simultaneously. So in the lift, what happens is that the molecule jumps not to the virtual state, which is in between 0 and 1. It jumps to the first one, that's first electronic state, and when it comes back to the lower level, the fluorescence is emitted, and that is being measured by the say ICC camera, which can then be quantified. And this is an example of a OH lift that's shown using laser diagnostics. So with this, let me give you a brief flavor of particle image velocimetry, which is making velocity field measurements. Here, the laser is operated in the dual pulse mode to get 2 frames here, and these frames are then divided into different interrogation windows, and then the correlation is found out between those 2 windows to get velocity vector in each of these cells, and as such, we would have got velocity in all of the in the entirety of the field. So laser Doppler velocimetry and relay are the point velocity measurement techniques, so which basically depend on creating these parallel fringes using two or more multiple beams intersecting in a control volume. So that's that principle. And lastly, for the suit, the laser-induced incandescence is used, which can make qualitative and quantitative measures of suit. And here the principle would be to excite the suit to a very high degree of temperature, like close to 4,000 Kelvin, and then measure the incandescence which is emitted from it to determine soot particles, volume fraction, and also the particle size. So, in conclusion, I would say that I have very briefly, it's not at all an exhaustive explanation, I very briefly described several laser diagnostic techniques that are implemented in combustion area, and for further study, the readers can just refer to these very nice seminal papers and books, and we'll take the questions at the end of all the panels. Thank you.
Thank you, Dr. Santos. Now I welcome Professor Kościelka from University of Technology, Poland. Dr. Kościelka is an associate professor in mechanical engineering at the Department of Dr. Kościelka is an associate professor in mechanical engineering at the Department of Sustainable Transport and Powertrain Systems of the Lublin University Technology, Lublin, Poland. His expertise concerns the modeling of gas and oil flows as well as tribology, mainly in application to the piston rings, a cylinder system of IC engines. He closely cooperated with industry in addition to the research on improving the design of the piston ring cylinder assembly. He was the leader of the projects in which and modular low-bed semi-trailers for long and heavy loads were designed and tested. I request Professor Kościelka to deliver his presentation. Professor Kościelka.
Yes, thank you. I can hear.
Yeah, I can hear you. Please continue.
Okay, thank you. The topic of my presentation, modeling of a piston rings cylinder system of combustion engines, is strictly related to my main research interests. Yes, and piston with rings in cylinder creates a movable seal of a combustion chamber. The main requirements for this system are high air tightness, small movement resistance, small oil consumption, high durability. It's evaluated that about 5% of fuel energy is used to overcome piston assembly frictional losses, while losses related to blow-by are estimated to about 0.5% of the total fuel energy. However, according to some sources and in my opinion, these losses are much higher in modern engine and in real engine operation in vehicles. What is more, they strongly increase as a result of wear. And next slide, please. It is believed that there is still a great potential to improve the engine efficiency and emissions through piston assembly improvement. Nowadays, the biggest effort is focused on reducing frictional losses while maintaining oil consumption, components life, and blow-by. It is assumed that 20% reduction in piston assembly mechanical losses results in 1.5% reduction in fuel consumption. And mathematical models help to evaluate the effects of different parameters, design, operational parameters on the performance of piston ring cylinder system and thus to improve the system design. Advanced model of a piston pack, like my model, consists of several submodels: gas flow, ring dynamics, ring lubrication, asperity contact, and other submodels. To achieve satisfactory results, all these submodels should be integrated. And next slide, please. In the gas flow submodel, it is assumed that gas can flow through volumes connected by orifices. Volumes represent inter and behind ring spaces, and orifices represent crevices through which gas can flow, like ring end gaps or side ring clearances. Extremely important is precise determination of the volumes of particular regions and cross sections of crevices. For these reasons, thermal deformations and wear should be taken into account. Gas flow through particular crevices is usually modeled as isentropic flow through an orifice or as isothermal flow. And thermodynamic parameters of gas in particular volumes are calculated taking into account energy and mass balance and equation of state. And next slide, please. Ring dynamic submodel led us to determine the axial and radial positions of the ring in the groove, as well as its ring twist angles. And next slide. Ring lubrication submodel can consider different regimes of lubrication. It can assume only fluid friction, or it can also consider asperity contact. And next slide. The main results of calculations include pressures in particular lengths, axial positions of ring in the grooves, gas flow rates in particular crevices as a function of crank angle. And next slide. In this slide, some results of simulations from the ring lubrication submodel are presented. In the upper diagram, we can see the maximum oil film thickness for particular rings, and in the bottom one, the wetted area of the ring as function of crank angle. And next slide. Now I would like to present some examples of model applications. Here is a typical problem of improving ring pack performance. The aim of this work was to reduce blowback, not blow by, and minimize the number of actual ring displacements in the groove. Sorry, could you give next slide? Oh, okay, thanks. I will omit the previous one. Blowback is the reverse gas flow from the inter-ring spaces into the combustion chamber. If you look at the lower left-hand chart, where pressures in particular inter-ring regions are presented, you can see that in some period of engine cycle, the pressure in inter-ring lengths, these blue lines, is higher than pressure in combustion chamber. In such case, in such situations, the gas flows from inter-ring regions to the combustion chamber. It's called blowback, and it's believed that blowback increases oil consumption and hydrocarbon emissions, and that's why we try to minimize it. The effect of different design variants was investigated during this work, and please look at the upper chart. Usually modifications which reduced the blowback, this red line in this diagram, increased blowback, blue lines. But finally, two solutions were suggested. The first one, which allowed us to eliminate the blowback completely, but at the cost of two displacements of the second ring in the groove, and blow by higher by 65%. And the second one, which did not eliminate blow by completely, but reduce it as much as 3.5 times in comparison to the initial version, and this version prevents the second ring displacements completely at the cost of blow-by higher by only 40%. And eventually, this solution was adopted by the producer. And next slide, please. And another application. The objective of this research was to evaluate how the different cores of pressure in homogeneous charge compression ignition engine with negative valve overlap, this is a green line in this upper left-hand chart, affects the ring pack performance. It was compared to the traditional spark ignition engines, and in this diagram you can see the indicated pressure for spark ignition engine at the same load, this brown line. And the main conclusions from this research were that the energy losses due to blow-by in HCCI engine are 100 higher than in SE engine. The energy losses due to friction of the rings in HCCI engine are higher by 7%. And the last very important finding from this research is that the energy losses related to blow-by are comparable to rings frictional losses, especially in the case of HCCI engine. And the next slide. Yes, in this very short presentation, I wanted to show that simulations are very useful and help to improve the design of the piston assembly. More details you can find in my publications, for example, that listed in this slide. And so thank you for your attention.
Thank you, Professor Kostyamkar. So we will come back to you. So our next panelist is Professor Shailendra Sinha. So Professor Shailendra Sinha is presently working as professor in the Department of Mechanical Engineering and also holding the portfolio of Dean at IIT Lucknow. He completed his BTech in Mechanical Engineering in 1989 from K-90 Sultanpur, ME in 1992 from University of Roorkee, presently known as IIT Roorkee, and PhD in 2008 from IIT Kanpur. He served in the industry from 1993 to 1996 at various positions and then joined IIT Lucknow as a lecturer in mechanical engineering in 1996 and became professor in 2012. His area of interest is IC engine, fuels, energy, vehicle emissions, combined power cycles, etc. He guided several MTech PhD students at IIT Lucknow and Dr. AEJKATU Lucknow. He published many papers in international and national journals, conferences, etc. He has worked at many administrative capabilities like additional COE, professional training and placement, and head of the department, etc. at IIT Lucknow, UP. UP State Engineering Entrance Examinations, various committees of the government of UP, and associate dean at KKTU Lucknow. So I request Professor Sinha to give his presentation.
Thank you, Professor David, for such a nice introduction and giving me a opportunity to share some of my views here. All of you from the morning are heavily loaded with all these technical discussions. I cannot wait to do you much about that, whatever the morning and all those things. I think you can assume it is a relaxation for you. So I just want to raise some issues. And as we have seen, what is the importance of so much heavy technical sessions and all those things. What is having from the every corner of the country, as we are listening nowadays, that diesel engines are not the future and it is just going to be obsolete. nowadays of the electric batteries are going to be there. But still, electric batteries, there are some challenges are there, some issues, why they are not going to be so much commercialized, what are the other infrastructure has to be developed. Whatever about the diesel engines, you can say about its low cost, or whatever the proven durability of the engines, it is still the first choice of the customers here to use the diesel engines. And I am definitely not worried about this, whether the diesel engine is going to be obsolete, because whatever the things are going to be happening, I am certain for many years, diesel engine is with us. But still we have to think about, if you want to align the diesel engine, what we have to do. And there all these technical sessions will raise their importance. What we have to do to limit the align the diesel engine. So very short, I will discuss some of the issues and just a very small thing, all of you are aware with this. I am not going to say much about that, but the types of fuel and what should be the combustion strategies, what those fuels are going to be there. Generally, we have talked about the automation or the petrol engines. Generally, the homogeneous carbureted friction is supplied, and high volatile and high self-emission temperature fuel is there. In the case of diesel engine, we are using the less volatile or completely low self-emission temperature, and just the thing is that we have to raise the temperature of the compressed air, and all those things are going to be there. Just to brief about that, what the inside the cylinder of the diesel engine is happening. Because what is there, we have to supply the liquid fuel that is going to be injected at a very high pressure inside the combustion chamber, and high pressure as far as we are moving toward the common rail or the heat injector, this high pressure is further increasing, and just to get a better combustion and improving the profile of the emissions that is going to be there. These are some of the graphs. All of you are aware what things are happening in the engine. It is the fuel is going to be injected, and that fuel is going to be prepared inside the diesel engine as a air fuel combustible mixture. And that is very important thing, because what is the preparation of that fuel, that is going to affect the performance or the, let's say, the emission, whatever is coming out of the engine. Everything is going to be depending upon that. So I'm not going to explain these stages there and all those things. Very important thing is where these things are going to be happen, how to save the engine, how we are talking about the electric vehicles, main culprits, the emissions which are coming out of the engine. If we are talking about the efficiency, we have reached to a maximum or almost very close to the maximum whatever is possible, but still a lot of work has to be done in the case of the emission to reduce the pollutants effect from the engines. And emission, particularly diesel engine, just from starting, all the fuel is going to be sprayed and how it is going to be mixed, that is going to affect the emissions. There the normal air mixture is going to be formed, or very lean mixture is going to be formed, or very rich mixture, where the smooth formation is going to be there. All those things are going to be just affected by the spray characteristics. Here just I have seen what is happening. When the fuel is going to be injected just from the drag forces from the surroundings of the air, that fuel is going to be break up into small droplets, what is atomization, that is further vaporization, mixing of air, and further it is going to ignite, and the further combustion is going to be taking place. So whatever the things that is happening here, some part is taking place inside the nozzle, whatever the condition, what is the turbulence created there, and how it interacts with the air, whether it is only motion of the air and all those things that are affecting the. These are the generally the pollutants we can categorize in terms of solids, liquid, or the gases. So they are solid organ infections, some fluid organ infections, some buccal infection, polynuclear aromatic hydrocarbons, and generally what we are from the category of regulated emissions. That is the LOX, if they are carbon hydrocarbons, who and the carbon monoxide. If we have to make the engine alive, we have to work on each of the sources where these pollutants are going to be generated. We have to do very small regions in the combustion chamber from these pollutants are going to be generated. So in short, just here I have made this slide just to make aware you get what are those regions where these different emissions are generated. Particularly, we see the hydrocarbon emissions. Certain carbohydrate region is going to be there. Whatever the oil impingement, what is the fuel impingement on the wall of the liner, undermixing of the fuel, which is later injected into the combustion chamber due to the low velocity of that, means some mixture is going to be there and some overmixing. Whenever it is beyond the flammability limit, then there is the formation of hydrocarbon are going to be there. And the major important thing, whatever the emission delay of the fuel, that plays a very important role in the formation of this hydrocarbon. Just here I have shown this. Similarly, the NOx particulate emissions, all of you are aware with this, where the regions are going to be there. If we talk about the NOx emissions, it is just where the more availability of oxygen, slightly near the stoichiometric pressure is going to be there, or we can say the high temperature region is going to be there. So we have to look after the regions where this NOx is going to be generated, where there is particulate matter, where particularly very big mixture is going to be there, soot is going to be formed, soot, the solids are there, and then the other whatever the some hydrocarbons, some volatile hydrocarbons that are going to be deposited or condensed over the soot, and particularly forming the mixture, particulate matter. These are some of the modeling where we can do. Display modeling is very important. We have to piston kinematics, what is the air motion, turbulence, similarly work out the transition, and finally when the combustion is going to be there, how the combustion is there, how the flame is affecting different regions, what are the regions are going to be there, where this falling. Suppose we see just here, what are the regions where the different pollutants are going to be formed. This is just a fuel spray shown, different color regions are there, this down region, basically the liquid fuel, and just near the liquid fuel it is a very high or rich mixture is going to be there. Then the soot formation is going to be started, NOx is just around the periphery where the high temperature is going to be available, oxygen availability is also going to be there. So these are some other things during the combustion of flame, how the emissions are going to be generated. This is a small slide showing you that.
So, Professor Sinha, so I think we can.
Okay. So these are just I am skipping the thing. This is just I have shown that how this soot is going to be formed. Just I am focusing on this in pollutant formation because only this issue is here, which forcing the government and other regulating authorities to put the electric material. And here some of the area which I find today's is going to be there. Whatever the new technologies in the field of the battery or in the field of the fuel cells, but that has to be very costly and has to be developed for certain types of things. So we have to reduce the emission, we have to optimize the parameters, some adopt of the treatment devices are there, development of alternative fuel is another thing, and whatever these things are going to be there, basically we have to look on how combustion is taking place and how combustion is affecting these things, and here the modeling comes into picture. Because what is happening, if we talk particularly about the IC engine things, you can say very advanced instrumentation, weather diagnostic and everything is available, optical window is there, optical engines are there. But to perform this experiment, that is a very expensive. Very expensive experiment, and just to reduce the cost of the experimentation, then it comes the modeling into the picture. First we do some physical modeling of the display formation, pollutant formation. Then we look into what is the optimum things are going to be there. And then better to perform the experimental stations over there so that we can reduce the cost of the total, that we can contribute to the other development aspects. of the country. But still, we can't say that the modeling is a very, very simple task. It is not going to be a simple task. There are certain limitations. The modeling, it involves the heat transfer, fluid, whatever the chemical reactions are going to be there, how the flame can capture oxidation. And at the last, whatever is going to be there, the computational tools available to us, whatever the software tools which are available to us, that is our limitations is going to be there. Computational time, whatever the selection of grid and all those things are going to be there. But definitely, all these techniques and this modeling will reduce the emissions in the engine, and we are sure that we are doing research in such a manner and just to small pockets where the emission is going to be formed, we have to take care of that, and this will just save the life or will save the period. Thank you. Thank you.
Thank you, Professor Sinha. So now so this was in the last presentation in our session. I request the audience if they have any question from the panelists. From any of the panelists, if you have any question, we can discuss the same.
One question to Mr. Thakur. Sir, you explained about railing and Raman and fluorescence. So, as in all the three phenomena are very much similar, but the excitation level and the de-excitation level. So, is it just the diameter of the droplet, or what is it that determines what scattering is?
It depends on the wavelength of the laser that you are firing. For example, in which clip you are firing at, say, 280 nanometer of wavelength. That is suitable for that wave molecule to go up from its zero state to 1%. So it entirely depends on the wavelength and also the target length.
So anyone else who is having any question from the panelists? Okay, so I would like to have a few questions from the panelists and more of private discussion with my colleague Gabriel.
Hello. So I would like to have a few questions from the panelists with my colleague Gabriel. So Professor Ramesh, I was just looking at your presentation and so how this thermodynamic model are
I'm not able to hear you clearly. Can you please repeat it, please?
how the thermodynamic models are beneficial in advanced engine modeling, advanced engine development.
Actually, see, thermodynamic models may not directly be applied. For example, if you have a CFD simulation running and you want certain boundary conditions, then the thermodynamic models can very easily use the boundary conditions for applying on your CFD model, so that your CFD model runs faster. I mean, it takes lesser time to run. That is number one. Number two, if you have a new concept, for example, a new concept of variable valve timing and things like that, which do not need very detailed local knowledge of the mixture or whatever, then thermodynamic models are very useful. Third use is that when you want to run a parallel simulation along with the engine, for example, in a hardware in the loop simulator, or in the case of an ECU, where in the ECU you want to make predictions of what is going to happen in the next cycle, thermodynamic models are very useful because they are simple. They are not very time consuming, but they are robust because they have been tuned with a lot of experimental data already. So as the engine is running, you can predict what's going to be the next cycle's ignition delay, or if I use this injection pattern, what will be the heat release pattern, and so on. And so you can use it to predict and control the next cycle itself. So these kinds of things, like hardware in the loop simulation or next cycle control, are easily done with thermodynamic models. Here, they have more use practically, I would say.
So, Professor Ramesh, I saw in one of the slides, I saw the code start approach in one of the slides.
Yes,
so, can you elaborate on that?
This is a typical application of a thermodynamic model to validate a new concept. So we were trying to start an engine at a very low temperature with with a low compression ratio. Low compression ratio obviously leads to low NOx. It was a low compression ratio diesel engine and had problems in cold starting. So what we were trying to see is how we can use the engine's compression work itself to raise the temperature of the charge. So it was a mechanism which allowed the charge to be repeatedly compressed rather than being exhausted during the starting period. That is, you don't have any fuel injection. You repeatedly recompress the charge. That is, compress the charge, take it out, put it back into the cylinder, and again compress the charge, so that you do more work on the charge and raise its temperature, and then inject the fuel and then start the engine. So this was first proven using a thermodynamic simulation, and then we actually made the mechanism. We actually incorporated on the engine and demonstrated. So you take it from a concept to an application. Have I answered your question?
Yes, yes. So, thank you.
Thank you.
I will come back to Professor Hume. I was just thinking like how these LTCs are normally difficult to operate at higher engine loads. How modeling and simulation work can be helpful in this regard?
Yeah, but the voice quality is very bad. Could you repeat just main part of your question?
Okay, you missed it. So LTCs are normally difficult to operate at high engine loads. How modeling and simulation can be helpful in this regard? How modeling and simulation can be helpful in this regard?
I'm sorry. Maybe you can text it. I completely can't hear you.
Yeah, can you hear me now? Hello? It is in the chat.
Professor Gabriele is speaking, Di Blasio. I texted on the discussion section.
Oh, yeah, thank you very much. And now it is clear. Yeah, actually, this is a very serious limitation of low temperature combustion because this is driven by chemistry kinetics. So combustion is very fast. Usually, we can assume that it takes place at a constant volume. So actually, the limit is from combustion is very short, and pressurized rates are high. So, but modeling can help because we are as even multi-zone models quite well replicate heat release rate. So we can simply test different procedures, different approaches to reduce pressurized rate, to increase combustion duration, like advanced thermal management, like variable stratifications, very good thermal stratifications, very good mixture stratification, very good reactivity stratification. So actually, there is a quite large space for modeling to increase to increase low temperature combustion regime to higher loads. I can say that this is a subject of many researchers because this is a really important issue of low temperature combustion.
Okay. Another thing, the quasi-dimensional approach and how it is beneficial in premix combustion. What is quasi-dimensional approach? In one of the slides I saw this.
Okay. Actually, multi-zone models are quasi-dimensional, and this kind of modeling is can be quite difficult for conventional combustion because it cannot replicate flame propagation. It cannot replicate fuel stream. But as low temperature combustion is premixed, so this quasi-dimensional approach can quite good simulate this type of combustion. So actually, the quasi-dimensional models developed together with low temperature combustion premixed concepts because they have some good properties like very fast operation. It can be run even in real-time mode, and that's why they are, let's say, beneficial for low temperature combustion, for premixed combustion.
Okay, thank you, Professor Ganesh. So I also request my colleague Gabriel if he is having some questions or discussion.
Yes. Thank you, Professor Shukla. So if there are comments from the audience, I have a couple of questions for Professor Zinkir. And this is about the use of alternative fuels in the marine sector, because it is well known that the marine sector use low-grade fuels, and I'm wondering about the use of alternative fuels in this sector. This is the first question. The second one is, what about modeling of multi-fuel combustions? This is challenging, and what can be the rule of a different simulation approach like LES or RNS, less or run simulations? Just your opinion about it.
Okay. Yeah, normally marine engines are using low-grade fuels, but after the International Maritime Organization's regulation in 2020, there is a sulfur cap regulation. After that, marine engines started to use ultra-low heavy fuel oil, ultra-low sulfur heavy fuel oil, marine diesel oil, and these are the conventional fuels for the marine engines right now. But for the alternative fuel perspective, marine engines mostly started to use LNG and methanol, and also right now there are some studies on ammonia, hydrogen, and there are also some marine diesel engines with LPG. So mostly the fuel is translated from heavy carbon fuels to low carbon fuels, and then zero carbon fuels. I think this is the answer of your first question. And for the second question, can you repeat again, please?
Yes, sure. This is modeling of multi-fuel combustion is challenging, I think. So can you give some opinion about, and if you can give some insights into the different simulation approach, like runs simulations or less simulations, but only just your opinion about.
Yeah, run simulation is for steady flows, and land simulation is can be used for more what can I say, flow change situation, so we can use lens at multi-fuel combustion situations. This is my opinion about simulation types.
Okay, thank you. And Professor Shukla, are there questions from the audience, or otherwise I have a couple of questions for Professor Aziz.
Go ahead. Please.
Okay. Thank you, Professor Zinger. And for Professor Aziz, so autoignition characteristics is a fundamental topic, obviously, and especially if you're looking at the application of zero carbon fuels like hydrogen. Can you provide more insights into this topic? And what about the impact of technologies like specific combustion architectures on the impact on the autoignition characteristics? Thank you.
Okay, thank you very much, Dr. Gabriel. So I think hydrogen is a promising. Talking about the hydrogen is a promising fuel for sustainable and zero carbon fuel. Although there's a lot of research actually have been done on hydrogen, however, we still lack of data on the understanding and how the fuel of this kind of new fuels like hydrogen behaves in the real combustion, in the real engine. Therefore, having the combination of the metal engine, optical engine, as well as numerical simulation, actually, we can have a better understanding. So, with this better understanding, actually, we can develop a high efficiency engine for hydrogen from these results. And talking about the what we call it, the diameter, or sorry, I think you're talking about the shape of the engine, or specifically maybe the combustion. I don't really get the second question.
Yeah, the second question is more about the impact of engine technologies on the autoignitions. That means, for example, in terms of combustion chamber shapes or piston bore designs and so on.
Okay, so when we're talking about the combustion chamber shape, actually, when I was in Lund, so we have tried quite many different combustion design, and we figure out there's actually impact the autoignition. Of course, when you have a smaller what we call it not a smaller, what we call it a higher compression ratio, and of course you have better autoignition if you are using the right fuel. But then when we take into an example of Volvo, actually, so they in 2017 they come up with the wave piston. So and they make a lot of study about this wave piston, and then they actually doing so much about the numerical study. And then finally, in the real engine, they figure out they have improve in the fuel consumption, which is fuel consumption reduced by 2%, and then the particulate matter have been reduced half actually. This is because the combustion shape in the wave piston helps improve the air mixing, and of course actually the piston shape actually also impact the location of the ignition of the fuel. Hope that I answered your question, Gabriel.
Thank you. This was the main point, the wave piston. This was also a question for the last speaker, Professor Sinha. This is a very hot topic, especially for compression ignition engines. Thank you very much for your nice presentation, Professor Aziz.
Okay.
The next one, since we are strict on time, I have a very quick question for Professor Santos. In particular, In the view of massive electrification of the transport sector, at least these are the recent guidelines from governments and so on. How can combustion peoples apply their experiences on those techniques to other topics, for example, on batteries and so on? Because the presentation was very interesting, a lot of techniques, and I'm wondering how can we use these experiences in other sectors?
Okay. Yeah. Considering that if all the vehicles get electric, get converted to electric, of course the techniques that were discussed to determine the flow and species mass fraction wouldn't actually work. But then there are a lot of other techniques to say which can be applied to determine the temperature at the surface. It could be application of say higher cameras and other diagnostic tools, say the depositions would come in handy there. But there was a serious question raised whether we have, in fact, enough materials in the world to convert all of the transportation to electric. So in that way, in that argument, even if we consider that if only a part of it is getting converted, then the conventional combustion is going to coexist. So in which case, these techniques would be still very, very relevant and would be important. In fact, going forward, they will be more relevant to assess the fuel flexibility and also to find out the alternate fuels for existing combustion techniques. Hope I have answered your question.
Okay. Thank you. Next question is for Professor Kozalka. I have some curiosity because the topic treated with the ring pads are quite new for me. Even if we are combustion peoples or engine guys, but piston rings are a very specific topic. But what can be changed when we use alternative fuels like, for example, again, hydrogen? And what do you expect would change in the ring pack configuration? And the first, this is just a curiosity. The second one is, can we consider the use of alternative fuels in modeling the ring packs? For example, you know that in diesel engine with inverted injection strategies, you can have oil dilution effects. Can we model this kind of phenomenon, or this is very challenging? Thank you.
Thank you. Well, I think that I do not model this phenomena directly, but well, I think I can consider this in two ways. First of all, I think that this fuel left on the cylinder liner can affect the oil viscosity. So I think I can modify the oil viscosity when the rings are going upwards. Yes, so this is one way in which this can be considered. And the second one, I think that I can consider this in sub-models in which I determine the thickness of oil film left on the cylinder liner above the top ring. So I use such very simple linear model of oil evaporation. So if you think that this fuel can make this evaporation faster, so I can just consider it in this way.
Okay, thank you. Yeah, very interesting. Yes, this is a good point. Thank you for this feedback. That's enough for Professor Kozalka from my side. I don't know if
so Gabriel, maybe we can proceed for the student session now because we have 45 minutes left now, and we should now finish the session also. So I and myself and Gabriel, we thank all the panelists for delivering their presentation. Now I request all the panelists to stay with us to evaluate the student papers now, student presentations now. So yeah, we can proceed for the student presentation now.
Okay.
Sorry, Gabriel, it was a question for me.
Sorry, no, sir. Professor Gojal, it was not a question. I was saying that this session we have to finish now and we should proceed for the student session now, where we need to evaluate the student presentations. And the evaluation sheets are mailed to you. The student evaluation sheets are emailed to you. Please check your email box so you will find it.
So I'm presenting on the topic 3D modeling of coaxial injectors for direct injection of methanol in large volume. So as you know, the methanol can be a jerk negative for the locomotive. So my research is based on the modeling of 3D modeling of methanol as a fuel for the locomotive engines. The objective of the research was to check the feasibility for methanol can be worked as alternative for the locomotive engine or not. So accordingly, we have seen the incidence phenomena of methanol using the simulation approach. So in the methodology, first we have collected a test data collections for the base model validations. After validating the base model with the 3D, we have converted that model to adopt the methanol. And after converting the methanol, so basically this conversion based on the modeling with the bundle. So after validating the model on the bundle, we have moved on the 3D. So you can see the base model having the 9 nozzles and the methanol plus diesel model having 5 for the methanol and 3 nozzles for the diesel. So how we have selected this 5+3 configuration that has been done from the bundle modeling. So these are the engine specification. You can see this is 16 cylinder engine. So now coming to the validation, this is the P-theta diagram validation. So for validating the models, we have taken the P-theta history and we have validated the trap mass by taking the initial, varying the initial temperature and the pressure. Accordingly, this model has been validated. And you can see with the diesel, the oxygen concentration, CO2 concentration, and the CO concentration, all were less compared to the only diesel. So in the starting, we have taken the 10% diesel as a pilot diesel to ignite the methanol. So the rest 90% was the methanol. So you can see with the methanol, the in-cylinder temperature raised to up to 2831 Kelvin, sorry, to 2600 Kelvin, and with the diesel, it is raised to 2831 Kelvin. So by injecting methanol, the in-cylinder temperature was reduced. So we can see that is because it is making more homogeneous mixture in case of methanol. So this is the conclusion. We can say by injecting methanol, since the more homogeneous mixture was found, and accordingly the in-cylinder temperature was lower, so it can be more good substitute to the diesels for the larger locomotive engines. That's all. Thank you.
Thank you, Dhananjay. Question from the audience?
May I have a question?
Yes, sir.
All right, so you're talking about the methanol. May I know what kind of injector you are using? Are you using the same diesel injector, or you have kind of special injector when you do your simulation?
Sir, for injecting methanol, we have used a coaxial injector, in which 10%, the 10% of the diesel quantity will be remain same for the igniting methanol, and the 90% of the energy basis of the diesel, we have taken the methanol. So both fuel can be injected simultaneously.
Okay.
Thank you. response, suppose, please start of the question.
So, good evening everyone. I'm Ashutosh Jaina from IIT Kanpur, and my topic is basically on gasoline compression ignition with narrow angle rate injectors. So, as we had also a very in-depth discussion on these things, like how the fuel reactivity actually governs your ignition delay. As you can see that for PRF 0 and PRF 60, the ignition delay will actually decrease as you move ahead with your equivalence ratio stratification. So, in nutshell, if the equivalence ratio is higher, the ignition delay for diesel and low octane gasoline is going to be similar. But with conventional diesel injector, the fuel always stratify near your ball periphery, and for your advanced injection timing, it may enter the squares. So what happens is the higher equivalence ratio is stratified here, which generates higher heat release rate. However, the lean stresses over here contributes to your hydrocarbon emission. So to this end, we realize that the injector geometry and the piston geometry needs to be changed in order to control the combustion. That is basically governed by your equivalence ratio and also definitely on your PRF, that is the fuel reactivity. So to this end, what we have done is we model a GDI injector. Basically, GDI injector works at low pressure, and that is good for your gasoline because you don't need that extent of atomization. So we validated the injector model separately and also the combustion model. For the result, I'll be explaining the result based upon the slice extracted from the piston ball. So we can see that for narrow angle injector, actually the fuel impinges on the piston bead and it moves the reverse way that we know from the conventional injector. It moves in a reverse way. It sort of destroys the conventional orifices that is common to your diesel. So what happens is the fuel re-enters from the top. In case of diesel, the fuel will impinge here and re-enter here. It may also go into the squeeze. But here we can see that the fuel actually re-enters from from the top and also from this vortices. So the ratio, homogeneous ratio is quite equivalence ratio is even. So due to the even distribution of the equivalence ratio, you can see that the black one is actually for the conventional diesel injector and the red one is showing for the middle grade injection. So due to the homogeneous distribution, not completely homogeneous but better homogeneous distribution, the pressure rise rate is controlled and the ignition is delayed somewhat. So we need to tweak with the injection timing to play with that so that we can manage the combustion engine and extract more power from the engine. That needs to be tweaked. So the conclusion of the narrow angle injector, the fuel can be confined inside the ball. So it could be investigated for the RCCI-like system where you can directly inject the low reactivity fuel for low load so that you can confine the charge in a smaller volume region. Like rate injection can do that around -65 BTPVC. So the injection the fuel could be confined inside, and the low load limit of the RCCI can also be extended by adopting this approach. So this requires sort of further both experimental and CFD, and we can technically extend the low load limit of RCCI sort of things. Thank you.
You talked about reactivity. What are the other factors? You talked about one factor on which it depends. What do you think are the other factors?
The other factors are definitely the fuel cycle number and temperature. Basically, if temperature is higher, the low reactivity fuel can approach the reactivity level of your high reactivity fuel. So the T5 diagram is very important to study the temperature and pipe distribution inside the engine. So yeah, definitely air heating. That's why we are using air heating in low reactive RCCI and GCI like engines to match the combustion quality of diesel.
In one of your slides, there was probably a recirculation zone. There was a recirculation zone.
Yeah.
Okay. at the edge of the engine.
Yeah.
So what is the reason for?
Actually, the reason is the swivel motion is outward. The centrifugal force of the swivel is outward, and the squeeze flow is inward. So there is sort of competition in between that. So the air motion tries to penetrate towards the bottom, and then it again rises due to the centrifugal force. The vortices is formed. This is true for the conventional diesel injector, but however for gasoline Nero injector, the fuel actually impinges downward and sort of destroys that vortices. So that is one of the observations.
Thank you, Ashutosh. The next presenter is Avinash Harsimran Kaur. Harsimran Singh. So, Harsimran, please. Can other panelists hear me? Are you able to hear me? I'm asking other panelists, are you able to hear me?
Yes, we are able to hear you.
Okay. We are having some problems with the projector. Just hold for a minute. So I request Harlan to speak for the next presentation.
Good evening, everyone. My name is Harsimran. I'll be presenting post presentation on potential of carbon reacting reducing carbon, hydrocarbon, and CO emission from gasoline compression ignition. As we know, in the fraction distillation process, we get a number of petroleum fraction having a range of different qualified, and within these fractions, we get a naphtha which is actually known as a low paying fraction and actually acts as a precursor to the gasoline. So if we see the future energy demand, there will be increasing amount of gasoline, however, there will be increasing amount of diesel. So whatsoever the naphtha which is getting consumed for the blending purpose of the gasoline, in the future it won't be able to use for the blending purpose of gasoline. So there will be a surplus amount of naphtha which whose volume will be gradually goes up to 23 quarterly in 22. So this naphtha can be used in gasoline compression ignition. GCI has a huge potential in reducing NOx and fuel emissions simultaneously. However, CO emissions are a different big challenge for GCI. This is because of the overall air mixture and also the presence of fuel in the sufficient devices region. So we investigated the different potential, different classes, different crystal geometry so as to reach the HCM geometries. This was the numerical investigation in which for that this is the motor validation in which we use two mechanisms, that is mechanism 2 and 1. Mechanism 2 was able to capture the experimental data quite well as compared to mechanism 1. Mechanism 2 was based on the three component primary reference group mechanism, that is isocane and heptane and chlorine. These are the different combustion models that we use, and in the previous analysis, what we found that within the crystal core geometry there is a dual vortex formation within the crystal core, and this the interface region of clockwise and anti-clockwise vortices forms a highly overlapping pixel packets, and this acts as a hindrance to the flame propagation, and this subsequently becomes the major source of HCMC emission. However, these vortices are important from the diesel point of view because diesel has a lesser volatility. And from the naphtha point of view, because naphtha has a higher volatility, we don't. There is no need of these vortex interaction. The mixing behavior can be sufficiently decided by the volatility of the fuel. So our motive was to intentionally remove those vortices, and with the Lambda geometry, there was no regular vortex interaction was observed, and as you can see, so those vortex interactions were quite able to remove the H6 emission from the interface region of the bottom, and as you can see that the flame current starts developing from the switch region, and it gradually enters to the center of the crystal geometry, and since there was no hindrance to the flame propagation because of the vortex interaction. So the conclusion with that the incidental flow structure must be correlated with the incidental combustion emissions. The interface region of the vortices are quite important and can be the potential region of HCMC emission. Barber geometry can be a good solution for reducing the HCMC emission from the GCA combustion.
Thank you, Dr. So I just have one question. So I probably missed some of them, but what kind of injection or mixing strategy you have adopted in your study is pre-mixed or direct injection?
It is a direct injection, but the injection time was about 20 to 21 minutes.
Okay. So what is the automation temperature for gasoline? What is the automation temperature for gasoline?
It's about 400 degrees.
So basically, by spreading emission, are you trying to maintain the rate of emission in the combustion chamber?
No, sir. Actually, the motive was to reduce those vortex interactions in the GCA mode. Because that was a necessity for the diesel case. Because diesel has a lesser volatility. But for the naphtha is actually act as a gasoline-like fuel, having octane rating of 70 or 75. But for that, the mixing is quietly controlled by the volatility because it is quite volatile. So we don't need those vortices for the mixing point of view. So that was the main motive of investigating this path of development.
Okay, thank you. So your alcohol, hydrocarbon, and carbon monoxide are they mutually independent? Separation of them, are they mutually independent?
Yes, I mean the formation of I can't.
Okay. And just one thing, this is the first time that soil has been taken from a negative sense. Probably, can you explain why the formation of soil or how is it affecting the formation of can you say probably in terms of time?
So the sperm was higher the sperm ratio that we took in this we took 1:2.23. This is the major range that we took in the design. So higher the sperm was, higher was the magnitude of those vortices that form clockwise and anti-clockwise vortices. So the vortex interaction that should be minimized in case of GCI conversion, not in case of diesel. was quite low at that fermentation region. And fermentation also acts as an indicator of low temperature. So lower the fermentation concentration, low temperature indicator, and that gives rise to the CNC location. So we got that. So the air-food ratio that varies. So for this that will vary. I mean, for the diesel engine, it keeps on varying from 80 days to 1 to 20 days to 1. So for this analysis, the AFR, I mean, we can't comment on this, sir, but there is some range that we can use.
Thank you, Hassan. Our next presentation is by Mr. Rohit Kumar. Mr. Rohit Kumar. So, the video will be displayed.
Good evening, everyone. Velocity measurements of surrogate inside elevated temperatures. Let's start with understanding the background of this work. Transportation fields are composed of several hydrocarbons and this makes it very difficult in easily understanding the combustion phenomena developing detailed chemical characteristics. One such composition of diesel fuel shown here. Over the years, from research, it has been shown that surrogate fuels could help in the combustion phenomena for transportation. Laminar burning velocity has been used in the formation of surrogate fuel as it holds information associated with the fuel emission. The main motive of this work is to explore and measure the burning velocity of surrogate fuels at elevated temperatures. The present measurements have been performed using an external heated returning channel method where air from an air passes through the heater which mixes with the incoming fuel at the infusion point. This air fuel mixture passes through diversion funnel and the heat is provided at the end of the funnel. Fluid stabilizes at the location where the burning velocity is equal to flame velocity. The flame images obtained from this experiment are shown over here and only the planar flame is visible for the measurement. At the location of planar flame, all the parameters are inputted in the modified mass integration to determine the laminar burning velocity. The uncertainty associated with the measurement comes out to be within plus minus 5%. For the target field formulation, this is a typical flow chart where it starts with a target field selection of target field, where the target property is selected, in this case is laminar burning velocity, and the rotation model, which in this case is an energy fraction mixing rule. This is the most accurate mixing rule available in the literature in comparison to the other two. Moving on to result discussion. At higher temperatures of 650 Kelvin and 560 Kelvin, an isotope automatically has a similar at different temperatures. Only at initial condition, the mechanism predictions are aerodynamic. In case of methyl cyclohexane, when we compare the reaction pathway diagrams at 400 Kelvin and 600 Kelvin, the active radicals HCl6, the elemental flux decreases by 28%. For the proposed surrogate, the composition is found to be more fractions of 10 to 10 plus and it shows good comparison with the gasoline as well as the Zanzi model as compared to 400, which is so many reactions. Apart from this, it also shows a good comparison with the commercially available gasoline reported in the literature at different temperatures. I thought it shows an accurate measurement at different temperatures. It also matches excellently with the. Thank you.
The projector is not available online. So the projector is not available online. So we can go ahead with the next student. The next presentation is by Krishna Kant. Please.
Without audio feedback, without.
This is normal PPT. You can proceed.
Good evening, all. Good evening, all. Myself Krishna Kant. I'm from IIT Hyderabad. The talk is on air-assisted liquid state network in infrared atomizer. So, as we all know, through literature that air-assisted atomization produce very fine droplets. So, this work is focused on analyzing the various flow types, air flow types in the air-assisted atomizer. A typical air fluid atomizer is shown here, and we have where we have an axial flow inlet and also a small amount of tangential flow inlet, and along with that we have a air flow inlet. And so in this presentation, we have used numerical work. So we are using a coupled level set viewer solver where we have improved we have improvement in solver by using the smoothing and close point search method. And this work is of a high pressure flow where delta P is of the order of 170 kilopascal and density ratio will be 78 and viscosity ratio is 10 to the power so viscosity ratio is 100. Mass flow rate ratio is kept as 1 and liquid fuel inlet is 12.2. 10 to the power minus 3. So and we have used a uniform mesh where so that the spatial resolution is close to 20 micrometer. And in this work, the main focus is to improve the Lisa model. So we have an improved density ratio. We have incorporated density ratio in the Lisa model. So we will be comparing the Lisa model with our simulation results and our improved Lisa model results. So what we observe is like when we have no airflow, then the deviation in the cone angle is very high. But when we have an axial flow in the sheet, then the sheets get squeezed up and the cone angle gets reduced. And thus, and similarly, when we have swirling motion in the air, with the airflow, then again because of the centrifugal action of the airflow, the cone angle gets raised. And because of the in the negative swirl action of airflow, the sheets start flapping, which is why you get very less breakup length in the negative swirl action of airflow. And constantly with with the airflow, the liquid sheet breakup constantly decrease with the air action of the air and liquid. And we can see that the Lisa model fails to predict in the high density ratio case. It is over predicting for high density ratio, but the improved model gives a better prediction for Lisa.
So maybe we can conclude now.
So yeah, conclusion is like for airflow patterns drastically affect the spray cone angle and breakup length, and the sheet thickness is close to 0.33 of the droplet diameter, ligament diameter is close to 0.33 of the sheet thickness, and the Lisa model overplays at high density ratio, and the two model better predicts. Thank you.
Your simulation are carried out at very high pressure. How do you plan to validate the market data available?
Yes, we have experiment performed at that high
at 168.
At the 178 also at density of 78.
Okay. And then we talked about state breakup. Can you bring out key dimensions parameters?
Key dimensions parameter which is the Reynolds number of liquid, very important in these atomization cases, and other Weber number also there.
Okay, thank you, Rohit. So our next presentation is by Mr. Krishna. Okay. Yeah, our next presentation is by Mr. Nasir Attal. Mr. Nasir Attal. It is one question.
Hello everyone, today I will present simulation and analysis of coaxial inject protein. For industrial industrial burners are often governed by instability. In order to adapt to sustainable fuels, it is essential to study instability. In the present study, we study the instabilities on a coaxial burner in a narrow flow band of 0.8 to 0.8. On the right, we can see the top view of the coaxial burner defined with three inlets. In the coaxial configuration, two types of flow structures are observed. PVB, ROM greater than 1, and CTRZ, ROM less than 1. ROM is directly proportional to the difference between center jet velocity and the co-annular jet velocity. We will soon see the flow configurations. However, for the time being, just remember that these two flow cases exist. The two destinations have been studied experimentally as well as numerically. However, in the present scenario, we have more on the numerical methods. In a previous study, we have compared various turbulent models and concluded that RSM is best for CTRZ and RNG epsilon is the right choice for PVB. Using the simulated results from these models, a more in-depth analysis is presented, which was not previously reported. Coming back to the flow configurations, the time average axial velocity contours are presented. The white region highlights the recirculation zone. In CTRZ, where co-annular and central jet velocities are similar, the radial pressure gradient is dominant and a single recirculation zone is formed. In PVB, as the central jet velocities increase, it penetrates the vortex bubble and results in formation of two recirculation zones on the either side of central jet. The bottom two figures show the time average axial velocity as viewed from the vortex core center. Two shear layers are present in CTRZ, inner shear layer and outer shear layer. However, three shear layers are present in PVB, inner shear layer 1, inner shear layer 2, and outer shear layer. We will now compare both the flow cases based on three major instabilities. The first difference, we have axial turbulent shear stress. The axial turbulent shear stress present near OSL in both the cases is due to the entrainment region. As in PVB, the axial shear present in ISL1 asserts the dominance of the central jet over the co-annular jet. Moving on to the second difference, as the pressure gradient due to rotational influence is strong, the swirl has penetrated inside the recirculation zone in CTRZ. However, in PVB, the dominance of pressure gradient due to entrainment does not allow the swirl to penetrate inside ISL2. The swirl influence only exists between ISL2 and OSL. For the third difference, we have to refer to the stability criteria provided by Relay and later modified by Coates. According to Coates, the zone that experiences negative axial vorticity is considered to be centrifugally unstable and is highlighted in blue in the contours. The major observation here is a single instability slope in the time average circulation graph is observed in CTRZ. While in PEV, two different slopes are observed between ISL2 and OSL2. Two different rates of centrifugal instability are observed for the first time in coaxial configuration. This fact thus emphasizes that the dynamics of PVB are complex, and the future goal is to decipher the physics in PVB in great detail. Thank you.
Hello, Nasir.
I'm not able to see the slides here.
Is not visible online. We can proceed for the next presentation. So, Vivek K. Presentation by Vivek K.
Hello, I will briefly explain my work on impingement atomization of Newtonian and non-Newtonian fluids. Background for the study is that a requirement for safe fuel to avoid leakage and for safer transport and storage. Gelled fuels have unique advantages over solid and liquid fuels. The bulk atomization of gel fuel is possible by impingement atomization, which is a conventional method of atomization in propulsion field. Here you can see a impingement atomization inside an engine. The methodology used is that Newtonian fuels like Jet A1 can be replaced by water for atomization study. So water is taken as a simulant here. A comparison of liquid sheet breakup of water and non-Newtonian carbopole gel is done from a high-speed shadowgraph images of the atomization process. We can see doublet atomization impinging jet atomization process in this figure. Two identical nozzles are there through which the liquid jet will come out and impinge onto each other and form a liquid sheet which further break down into smaller fragments. The liquid sheet breaks up after a length which is termed as sheet breakup length. The results of the study is that the liquid sheet is broken down through a following injection pressures of 19 kPa to 384 kPa. We can see at lower pressure the sheet is visible and there is no sheet disintegration at the edges. As the injection pressure increases, we can see that sheet is disturbed and at a high pressure of 384 kPa we can see that fine atomization of fuel or water is happening. For the same case, when we take a carbopole gel, we can see that at a pressure of 1643 kPa only, we can see fine atomization. This is because of the high viscous nature of the gelled fuel. The sheet breakup length, as the Weber number, increasing Weber number, is found to be sheet breakup length will decrease with increasing Weber number. Liquid breakup seen only at very high pressure for carbopole gels compared to that of water. Thank you.
Vivek, are you online?
Hello, I will be presenting the topic impinging jet atomization of nanomobile water solution.
So the next presentation is also by Vivek K.
Hello, I will be presenting the topic impinging jet atomization of nanobubble water solution. The background of motivation for the study is that the presence of nanobubbles are shown to improve the combustion efficiency of fuels, and the fuels like kerosene, gasoline, diesel, etc. can support the nanobubbles on oxygen or air. In this image, pure water. Hello, I will be presenting the topic impinging jet atomization of nanobubble water solution. The background of motivation for the study is that the presence of nanobubbles are shown to improve the combustion efficiency of fuels, and the fuels like kerosene, gasoline, diesel, etc. can support the nanobubbles on oxygen or air. In this image, pure water and a nanobubble containing water is shown in two beakers, and the nanobubble is shown to scatter lights when a laser light is passing through both the containers. This is the container with nanobubble water. The scattering we can see here, we cannot see. The methodology used for this atomization process is that first the nanobubbles are generated inside the water, and the water sample is tested for the concentration and size of the nanobubbles by nanoparticle tracking analysis. Then nanobubble water solution is atomized by impinging jet atomization, which is a conventional atomization configuration used in propulsion field. And the liquid breakup characteristics with this configuration is studied and compared with that of the impingement atomization of water. The impingement jet atomization consists of two identical nozzles through which the liquid will come out and impinge onto each other and will form a liquid sheet which further disintegrates into smaller fragments. The results we found is that the mean bubble diameter, nanobubble diameter, is around 114.9 nanometers, and particle concentration is around 1.49, 10 raised to 7 particles per ml of water. At different injection pressures from 13 kilopascal to 318 kilopascal is tested, and the atomization is shown in these figures. You can see that at pressure of 318 kilopascal, very fine droplets are being formed. And using the same configuration when we atomized water, the same range of injection pressure, 19 kilopascal to 380 kilopascal, we can see atomization fine scale is happening at 384 kilopascal. So both are having same mode of atomization. Conclusion: the sheet breakup length is found to increase with the increasing Weber number for water. The nanobubble water solution is found to atomize in a similar degree at lower pressure compared to water. Thank you.
Vivek, thank you. Vivek, are you online? Okay, I don't think he is online. So I request all the panelists to send their evaluation sheet for the students. Please note that one of the students, paper number 11, Rahul Kumar Singh, he was absent and he did not present his work. So you can omit that. You can omit the evaluation for Rahul Kumar Singh. Vivek K, are you there?
Am I audible?
Please unmute. Am I audible? Yeah, now you're audible. So I request panelists if they have any question from Vivek. Okay, Vivek, then thank you.
Thank you.
I request all the panelists to send the evaluation sheet for the students. Please note that Mr. Rahul Kumar Singh, we need to omit this decision. And so my colleague Gabriel may conclude the session and thank the panelists also. Gabriel?
Yes, thank you, thank you. So, we are close to the closing remarks, or for the. Thank you for your active participation and inputs from this session. Thank you to the panelist speakers for bringing their expertise and experiences around this section and engaging in fruitful and constructive and open exchanges. Special thanks to my colleague Professor Shukla, conference chairs, organizer, for the excellent management of the conferences, notwithstanding the pandemic conditions worldwide. Thank you for the opportunity of assisting in hybrid mode in a high-quality debate, demonstrating that, as always, there is still room for improvements. I would encourage you to remain engaged and constructive and contribute to propulsion and mobility challenges. So let me conclude by thanking all of you again for your time and valuable insights. We look forward to welcoming you again next year. Thank you.